Research chemists today are faced with a variety of problems, challenging problems, stimulating problems, whose solutions may be important to us all. Charles Moffat is such a chemist. He works at Dow Chemical's Research Laboratory in Wayland, Massachusetts. This is an important day for him. Through weeks of careful work, he has separated the major component of an extract from a mold culture isolated from African soil. He has used thin layer chromatography to separate the sample. He uses a suction pipette to pick up the alumina strip containing the unknown compound. When collected, his analysis will begin. And what was a strip is collected in a small receptacle. The receptacle is connected to a collection vial. The solid mixture is then washed with ethanol, which will dissolve the organic compound. Although the solid is held in place, the liquid can drain into the vial, carrying the organic compound with it. This is done so that the compound can be analyzed to determine its molecular structure. After the solution has been collected, the sample must be separated from the ethanol. This is done through evaporation, using a rotary evaporator. Heating the vial causes the ethanol to be driven off, thus causing the sample to be deposited on the sides of the vial. From there, it can be removed mechanically, so that it can be analyzed. The process is straightforward, and it permits the researcher to gather small samples of compounds, sometimes very small. In this case, only 4 to 6 milligrams of the pure substance have been isolated from the raw sample given to Charles. The modern chemist relies heavily upon physical instrumentation to assist him in determining the structures of complex molecules. No longer must he wait days for the classical wet analysis to yield pertinent information. No longer does he need large quantities of a sample. A sample of 4 to 6 milligrams will be plenty. Charles is taking an infrared spectrum of the unknown compound. By determining the position and intensity of the infrared absorption bands, he can assign certain functional groups to the molecule. To his trained eye, the spectrum immediately reveals that the sample has a hydroxyl group, a chelated carbonyl hydroxyl grouping, and possibly an ester functionality. The sample is extracted from the infrared pellet. An ultraviolet spectrum is also taken, suggesting a xanthone derivative. Charles feels he requires further analysis of the sample using other techniques. He calls in a nuclear magnetic resonance spectroscopist and shows him the data, which he agrees is informative, but far from being complete. The nuclear magnetic resonance spectroscopist is briefed thoroughly, and Charles identifies both his conclusions and what inferences he can make about the substance. Even with modern analytical techniques, determining a complex molecular structure can be like assembling a jigsaw picture, attacking one part at a time, especially when working with a small sample. The sample is dissolved in deuterodimethyl sulfoxide and is inserted into the nuclear magnetic resonance spectrometer. It is swept over first 1,000 hertz and then 500 hertz sweep widths. In this case, the spectra are very noisy, as expected, due to the dilute nature of the solute. As a result, only limited information could be obtained. The spectroscopist has worked with easier samples. He can only bring in a highly preliminary report, offering more clues than firm conclusions. With this sample, the spectroscopist feels that there may be important signals hidden within the noise, signals that must be ferreted out. Because of the low signal-to-noise ratio, the nuclear magnetic resonance integrals and peak multiplicity assignments are very tenuous. There appear to be two methyl groups, one of which could be methoxyl, due to its low field position, and 4 aromatic or olefin protons, 2 of which could be coupled. Certainly, more work will have to be done. A mass spectroscopist is next asked to assist in solving this structural problem. Not all of the pieces of the puzzle are together yet. The researchers decide that the sample will be analyzed by mass spectroscopy after the final nuclear magnetic resonance data has been obtained. Back to the analytical laboratory. The sample is reinserted into the nuclear magnetic resonance device. This time, however, the nuclear magnetic resonance signals will be given a different treatment. The nuclear magnetic resonance instrumentation is coupled to another device that will further refine the signals. An electronic computer specifically designed for laboratory use. The computer used for this analysis is a Digital Equipment Corporation PDP-12 LDP computer. It can be used in a very effective way to enhance the signal-to-noise ratio of these signals. A technique known as signal averaging is used, in which the spectra are scanned repetitively, stored in the computer, and averaged. The noise, being random, averages out. The signal-to-noise ratio is increased as the square root of the number of scans. 64 spectra were summed, giving a theoretical 8-fold increase over the original. Information normally lost in the noise can be extracted easily. Next on the agenda is mass spectroscopy. The researcher prepares for direct sample insertion. The sample holder must be heated in a flame to burn off any old sample. A small amount of the sample to be analyzed is then placed in the now clean sample holder. This assembly is then inserted directly into the heated inlet system of the mass spectroscopy equipment. The technique of mass spectroscopy is another powerful tool that will help fit other pieces into the jigsaw puzzle of the sample's molecular structure. He then activates the instrument to analyze the sample. This powerful analytical technique helps determine many salient features of a sample. This equipment, too, is connected to the computer. The PDP-12 employs a special computer program, MASH, to perform its mass spec analyses. For Charles's sample, 10 mass spectrometer scans are taken at different instrument settings. The computer communicates more than one way. Within 15 minutes after sample insertion, the teletype prints out data, calibrated data on the sample. No one analytical technique has all the answers, and solving a problem of this type requires an in-depth discussion among all those involved. The nuclear magnetic resonance spectroscopist has much more detailed data now, thanks to his computer analysis, as he shows Charles. The averaged data are much clearer and reveal new details that were previously lost in the noise, which is even more evident in the expanded form. 2 small peaks are now revealed that were previously buried in the noise. As is easily seen by comparing the averaged spectrum with the original. The nuclear magnetic resonance time averaging results are put on the blackboard, as are those of the mass spectroscopist. The final structure of the sample must be consistent with all the spectroscopic observations. Just as the plots imparted information to the nuclear magnetic resonance experiment, so the computer printout helps the mass spectroscopist. The researcher in this case uses his printout as a worksheet and roughs out structural diagrams on it. More pieces of the puzzle have been uncovered. The data show that the sample has two methyl groups, one most likely attached to oxygen, the other located on an aromatic ring J-coupled to more than one adjacent aromatic proton. A decoupling experiment shows the aromatic protons coupled to the methyl are also coupled to each other by 3.2 Hertz, and therefore exist in a meta-relationship and ortho to the methyl. The two remaining aromatic protons form an AB pair. Coupled by 9.1 Hertz, they must be ortho to each other. The spectra reveal two hydroxyl resonances at 10.13 and 14.6 delta, the latter being the one that must be bonded to the carbonyl, as originally suggested by the infrared. The parent ion has a mass of 300. The molecular formula is established as C16H12O6. The base peak of the mass spectrum corresponds to loss of methanol. Such a dominant loss is highly characteristic of salicylate esters. Other prominent peaks at 240, 212, 184, and 156 are derived by 4 successive expulsions of carbon monoxide. Cleavage with loss of methoxide ion is significant. And again, the fragment produced undergoes 4 consecutive losses of carbon monoxide. Charles feels that there is but one structure consistent with all the observables: 1,7-dihydroxy, 8-carbomethoxyl, 3-methylxanthone. The jigsaw puzzle is solved and complete, and a structure has emerged. The structure of a complex and potentially important chemical. It could become the basis for a new medicine. Through modern technology, Charles has had his problem solved efficiently and rapidly. As he enters the results in his experimental notebook, Charles reflects how much more work he can accomplish now than he used to be able to. Modern equipment permits him more time for experimentation and permits more experiments to be run in the same period of time. And with as much or more accuracy than ever before. True progress in today's chemistry.